In algebra, the fundamental theorem tells us a polynomial of degree 10 has exactly 10 roots. But when we look at a graph and see fewer x-intercepts than the degree, it means some roots are hiding in the complex plane. Visualizing complex roots requires looking beyond the standard x-intercepts. We look for the turning points or wiggles in the graph that fail to reach the x-axis, indicating where complex conjugates reside. Let's define our core concept. A higher degree polynomial like this quartic function may not cross the axis for times. We define its roots as the values of x where x equals 0, even if those values involve the imaginary unit I. Intuition suggests that as we modify a polynomial's coefficients, its comps move up or down. When a local maximum moves above the axis or a minimum moves below it, two real roots merge and then vanish into the complex plane. To truly see these roots, imagine the x-axis is just one line on a flat complex floor. The polynomial is a surface above this floor. The complex roots are the specific points on that floor where the surface height is 0. By breaking a higher degree polynomial into quadratic factors, we can see why it doesn't touch the x-axis. Each factor represents a pair of complex roots that we can extract using the quadratic formula. Let's work through an example. For x to the 4th minus 1, the graph shows two real roots. Since it is degree 4, we are missing 2. We use the real roots to divide the polynomial and find the remaining factors. We divide the original polynomial by the factors created from our visible x-intercepts. This leaves us with a quadratic expression, x squared plus 1, which represents the hidden part of the graph that doesn't touch the axis. Solving the remaining quadratic gives us our complex roots. In this case, x equals plus or minus I. We can now plot these on the complex plane, showing they are perfectly balanced around the real number line. Consider a cubic function. The graph crosses the x-axis once at x equals 1. Because it's a degree 3 polynomial, we know there must be two more roots. That a flatness of the curve near the axis hints at their location. After factoring out the real root, we are left with another quadratic. Applying our algebraic tools, we find the complex pair. All three roots together satisfy the degree of the polynomial, completing our analysis. To summarize, always check the degree first to know how many roots to expect. Count the real intercepts on your graph. The difference between the degree and the intercepts tells you how many complex roots exist. Remember, complex roots always appear in conjugate pairs. If you see a dip in a graph that doesn't quite reach the x-axis, you are looking at the visual influence of complex numbers on a real-valued function. Here is a quick challenge. Look at this degree for polynomial. It never touches the x-axis. Based on what we've learned about pairs, how many complex conjugate pairs must it have? Since the degree is 4 and there are no real intercepts, all 4 roots are complex. This means there are two distinct pairs of complex conjugates hidden within the geometry of the curve. You now have the tools to analyze higher degree polynomials both algebraically and graphically. Understanding the relationship between intercepts and complex pairs is key to mastering polynomial behavior. Generated by Vision Solve AI.